Very big thanks that you explained the concept so clearly in the previous lecture. And now I have the daunting task of telling you all the technical details. So um, you can prepare for that. It will be way more technical. And unfortunately, it's just necessary because if you want to do computations, you have to learn about the techniques. But first, there are two short questions from the previous lecture. Let me try to quickly answer them. There's a question, why can't we impose the GR reaches the GFP in the UV? And there was a short sketch by Alessia. Basically, the reason is that Newton's coupling is repulsive. And this means that if you want to get an interacting theory of gravity, it's just there's no trajectory which goes to positive Newton's coupling. And then there's a question, is there any relation between the theta and the dimensions? The signs of them are related to the relevant or irrelevant as discussed. At the Gaussian fixed point, yes. At an interacting fixed point, the problem is that, well, you're interacting, so it's not only the mass dimension that accounts towards the critical exponent, but also the derivative. Can you please? Okay, thanks. And also the derivative of the anomalous dimension that you have to take into account since it's not vanishing. I hope this answers the questions. So let's get started in discussing how we can compute these non-perturbative beta functions. And as Alessia mentioned, the tool that we will use is called the functional renormalization group. And we'll see what the functional means within these 1.5 hours. Let me open my notes. Okay, so since we already had a lot of discussion about RG in general, I think I can skip the general blah blah and head right into the meat of it. So in the end, but still let me repeat the main point. The point of RG is we want to relate the physics of different scales, right? If I want to describe the physics of this table, well, the natural scale of this table is, let's say, 2 meters, all right? So I should describe this table in terms of objects that are of this order of length. I can also describe the same table by describing all the individual atoms in here, but it's very complicated, right? So the dynamics of these atoms is just completely different than the kind of coarse-grained description of this table. At the same time, if I want to zoom out a bit and I consider the Earth, well, certainly this table does not play a role for the Earth itself, right? I mean, at the exact level it does, but for all practical purposes, it does not. And this kind of decoupling is one of the fundamental ideas that go into renormalization group. Okay, so kind of the key point about functional RG that we will see is that we can do non-perturbative renormalization group. So if you say non-perturbative, what you should think of is, for example, really non-perturbative as e to the -1 over g squared, where g is a coupling. So something like an instanton maybe, but also all order effects if you would have something like a rational function. So these are the things that you should have in mind when we talk about non-perturbative effect or non-perturbative terms in beta functions. Maybe quick thing to stress is this functional RG is a continuum method. And it's of course not the only method that you can do non-perturbative physics with. Another very successful is of course the lattice. So lattice QCD, very successful in describing basically all of QCD except for some regimes, maybe at finite chemical potential. But there's certainly also limitations there. Sign problem, right? If you know a little bit about the lattice, there's a huge issue to solve. Yeah, so what you should keep in mind here is that different methods have different advantages and disadvantages. And in the same way, the functional RG has advantages. For example, that chemical potential is not a problem. There's no sign problem. But we also see that there are some disadvantages that the lattice maybe does better. So in the quest to describe a specific quantum field theory in a non-perturbative regime. Ideally, you come from different directions to also check that what you're computing is under control. Good. And yeah, for this today, we will just talk about the functional methods. And I think Alessia already briefly mentioned it. I will discuss Euclidean signature now. So think of it as Rick rotated, and we worry about the back rotation later. Actually, is one of the open problems here, but we'll get to there. So what's the starting point? The starting point of QFT is the path integral, usually, right? At least for me, the starting point of QFT is the path integral. And so in a sense, the kind of thing that we want to worry about in the end, that has been mentioned also in several lectures this week already, is the effective action, right? So the effective action is somewhat like the classical action, but it includes all quantum effects. So if we can compute the effective action, we have basically solved the theory. We know essentially everything about it. So in the first few minutes, I want to quickly derive, maybe as a reminder to you, how you get the effective action from the path integral. And then we will mimic this derivation to derive the functional RG equation. Okay, so a lot of words. Let's get finally into some equations. So the path integral, let me call it z of some source j. So how is it defined? For now, I will just discuss a scalar field. For simplicity, you can generalize everything to basically any field content with the usual caveat. So if you have a gauge field, you need gauge fixing, and for the F-Bobov goes, as also Luca mentioned. If you have fermions, you have to worry about anti-commutation. So lots of fun. We will not do that. Good. So what do we have? We have a normalization constant we don't worry about. Path integral over scalar field phi. And then there will be an action, a microscopic action S of phi, and a source term. And here you see that I'm in Euclidean signature because there's no I in front of the action, but a minus sign. Good. Now, you certainly know that the path integral contains divergences that need regularization and renormalization. For now, in all of what I'm writing, I will assume that there's some regularization in there already, maybe by an explicit cut of lambda, but I will not write it just to not clutter the notation too much. Good. What can we do with this path integral? Well, we remember the lectures by Anna. Scattering amplitudes are really important in description of quantum field theory, also connection to experiments at the LHC maybe. There you can measure scattering cross-sections. And to compute these scattering amplitudes, we're interested in correlation functions, right? So something like an expectation value of n fields with a source j. How is that defined? Well, you take a 1 over path integral and then the nth functional derivative. Of the path integral. Okay. So what does that entail? Well, if we just plug in the definition, this is something like the path integral with n fields inserted. And now let me be a bit time saving and indicate this integral over x just by a circle to save time and space. And then we have to divide this guy by z. Okay, so maybe some quick examples. Of course, if you have 0 fields, then you just get a normalization condition that the expectation value of 1 is 1. Not very interesting. If you have one field, that's kind of important. This will be the mean field, or also called vacuum expectation value. And then if you have two fields at x1, x2, this will be the propagator. And propagator, if you, well, probably you know this, it splits into a connected piece and then the product of expectation values. And then if you continue inserting more and more fields, of course, you can play the same games. We'll not write that down. However, the kind of key message why I'm writing this down is that also for higher order correlation functions, you have to split into a connected piece and then correlation functions of lower order. So you see that this path integral is not really storing information efficiently if you start listing correlation functions, adding more and more fields. So somehow this product of expectation values is redundant information. And first step to get rid of this redundant information is to introduce the Schwinger functional. Right? So we kind of want to only get this connected piece from a functional. For that, we introduce the Schwinger functional, W. That's simply the logarithm of the path integral. Okay. And with this, how do correlation functions look like? So now it's actually just a connected piece, and that we get from the nth derivative of the Schwinger functional. And I will often write this just in this way. Once again, to save some writing. And then I have not shown you that just because of lack of time, but you can convince yourself that if you, for example, compute a two-point correlation function, you insert a definition W is log Z into this expression and compare it with this expression above. This indeed just gives you the connected correlation function. Maybe one more thing in terms of notation. I will often use the propagator, which is just the second functional derivative of the Schwinger functional, and call this G. Okay, so Schwinger functional, nice, gets rid of some redundancy. But then if you play around a little bit with the Schwinger functional, you will notice that even that has some redundant information, and you can actually go one step further to get rid of even that redundant information, and that will lead us to the effective action. And the effective action is the one-particle irreducible, the generating functional for one-particle irreducible correlation functions. Good. So how is the effective action defined? Let's write it over here. And I will use the letter gamma for this. And notice now gamma is a functional of the expectation value, not of the field that is in the path integral. How is it defined? You take the supremum over all sources of the expression, well, the source term, so integral over x j phi minus the Schwinger functional. Okay. And I will sometimes just write that as, so if you take the supremum, the source will be the supremum source. This guy actually now depends on the expectation value. And then minus the Schwinger functional at, actually this, sorry about that, this should be phi. And also the Schwinger function is evaluated at the supremum source. So far just definitions. So you have to kind of, you either know or you have to believe me that this is useful. Why is it useful? Well, now connecting to what Anna said about scattering amplitudes, if you use the effective action to compute correlation functions, for any amplitude you want to compute, you only need tree-level diagrams, right? So it's very important. If you, say, do a 2-to-2 scattering, right? Let's say only S-channel. You have maybe something like this, some propagator and some other field. You might also have a contact term. Good. So you have these two diagrams. If you do perturbation theory with your microscopic action, you will also have to introduce loop diagrams, right? So maybe for this guy, you would also have to include a propagator correction and infinitely many more terms. And the point is, if you now use the effective action, these are already all included. You only have to compute this guy, and you're done. Okay, so very powerful. All quantum effects are included. Now, of course, there's no free lunch, right? Computing this effective action is very hard because it is equivalent to computing all loop diagrams. So certainly it cannot be an easy task to compute this guy. Okay. Any questions so far? Good. So let me move over here maybe. So let me maybe briefly discuss what I claimed here. So maybe some properties of this effective action first. Maybe the first point to convince yourself is that the conjugate variable of this Legendre transform of J is indeed the expectation value. And you can just pick up any book on Legendre transforms and check the definition. What is the definition of conjugate variable? You plug it in and you see it's indeed like that. So basically, phi, which is now the conjugate variable to J, by definition is you take the original functional, which is this W, you evaluate it at the supremum source, like this. And you just plugged it into the definitions that I wrote down, and you see indeed this is just the expectation value at the supremum source. So indeed, the expectation value is the conjugate variable with respect to the source. Maybe more interestingly and more importantly, what is the one-point function of the effective action? Right, so now I'm using the same notation that I told you about over here. Functional derivatives will just be superscript in brackets. So this guy is just the gamma d phi. I just use the definition over here. I will see this guy, so the single phi. I will take a derivative of the source, and I will take a derivative, or well, a combined derivative of this Schwinger functional because the supremum source depends on the expectation value. And if you do that, first get J sub from hitting the individual phi, and then you get a derivative of the source and two terms. You get a phi from the first term, and then the derivative of the Schwinger functional. And now you check definitions again, and you see, well, this guy is just, well, you see it here, it's just phi, so this bracket vanishes, and you get that basically equation of motion that you derive from the effective action is just sourced by the supremum source. So these are the quantum equations of motion for the mean field. Let me maybe write it down. So these are the quantum equations of motion. Good. Now, a third thing which I want to briefly discuss is very important property. What is the two-point function of the effective action, right? Okay. And I think due to time reasons, I will not show you why it is, but you can convince yourself, and it will be actually in the lecture notes. This guy, if you invert it, you get the propagator. As very straightforward calculation, just using the definitions of the individual functionals. Good. Let's go maybe over here. Good. Now, I told you a little bit about this effective action, and I still didn't tell you how to compute it, right? So it's all nice, but in the end, it's still kind of defined by the path integral in the end. So I take the path integral, I take a logarithm, I take the Legendre transform. So yeah. Kind of, yeah, I have to extremize this expression. Yeah, by changing J. Yeah. Yes. Yes, exactly. It's exactly this two-point function. Yeah. Good. So the task for me now is to tell you how we actually compute this guy, right? The effective action. And maybe the first try that you can do is, can you relate it to the path integral directly? Yes, you can. Once again, details will be in the lecture notes. Don't want to show it. But what you end up with is, well, some kind of equation. So let me maybe write that down. So you can write an equation of this form. You have the exponential of minus the effective action, and you can relate it to a path integral involving the microscopic action and the derivative of the effective action. So you see it's kind of a differential equation for this gamma. Still very complicated. There's still a path integral that we have no clue how to solve. So maybe it's not the best strategy. But for some theories, it is actually a good strategy. You can systematically solve this equation by expanding in vertices on powers of the field. And then you will get what is known as Dyson-Schwinger equations. And these are very useful, for example, in the context of QCD, where you can make some progress. So usually it works very well in asymptotically free theories, but it's not so good if you don't really know what the microscopic action is. And this is unfortunately the case for us in gravity. So we still kind of haven't found a way to compute this gamma, so this seems not promising. So let us finally go towards this functional renormalization group. I first want to tell you a little bit about the concept, and then we try to derive an equation to arrive at this. So in a nutshell, what is the basic idea? The basic idea is that not only physicists, but also everybody has some problems in solving integrals, right? Integrals are really hard. What we are really good at is solving differential equations. Okay, so differential, no? Okay, let's say like that. Solving differential equations is kind of more systematic than solving integrals, right? So for integrals, there's no general technique how to solve them. Whereas for differential equations, at least in principle, you can throw it on a solve or a Newton-Raphson method or whatever, and you get some numerical solution, let's say, in the worst case. Maybe get some analytic solution. That's also possible. But certainly we have a lot of machinery to solve differential equations. So let's maybe try to, instead having to solve an integral, formulate everything in a differential equation. Okay. And to make it a bit more concrete, let me make a sketch. Okay. So let me sketch the space of all action functionals, right? So any point in the space is one specific action. So maybe some microscopic action over here, and then the effective action is now phi over here. And the task is now to go from here to here. And wouldn't it be nice if we can define something like an interpolation? Yeah. Okay. And then maybe we can even define a differential equation whose integral curves are these connections. So, well, this is exactly the idea of the functional renormalization group, right? So what we will introduce now is what we call the effective average action, gamma k. And it's constructed in such a way that, so we have this kind of, well, parameter of the curve, let's say like that, where if I send the parameter to infinity, I end up with my microscopic action. And if I send my parameter k to 0, I end up with the standard effective action, which has all the nice properties. So it would be nice if such a thing exists, and it does. And we'll derive an equation for this guy. And yeah, for doing so, we will basically mirror the discussion of the path integral. We start there and go through basically the same steps and end up with a differential equation for this gamma k. Any questions so far? Okay, very good. So how do we do this? What we will do is, so essentially what this, should maybe say that, what this idea implements essentially is the Wilsonian idea of integrating out modes, shell by shell. So what is behind this is you want to do the path integral, but instead of integrating out all the fields in one go, you say, well, let me integrate out a little bit at the high energies, and then a little bit more, a little bit more. And you successively integrate out modes with lower and lower momentum. Okay? This is the basic idea that's behind this picture. How do we do that? Well, first step, we modify the path integral by a suppression term. So we introduce now zk, where k is exactly this parameter of the curve. This will in the end be something like a momentum scale, which separates infrared from UV. And how does the modification look like? Well, I just told you I want to integrate over everything that has momenta larger than some reference scale, which I pick k, and the exponential is unchanged. So in the end, the zk only includes field modes which have high momenta. And then, of course, if I send k to infinity, nothing happened. I can do a set point approximation, so I get classic action. And if I have k equals 0, I've just integrated over everything, and I get the effect, right, the full path integral. Good. So now we have to discuss a little bit how to implement that. If you implement this sharply, with a sharp cutoff, you say, I only integrate out momenta larger than k, and I do not integrate out momenta smaller than k, This is maybe not the best way because then you break a lot of continuum symmetry. Certainly gauge symmetry is broken by that. You can do that, but it's not what we want to do. What we want to do, well, if you do that, you get a different functional RG equation, which goes under the name of Wigner-Houghton equation. What we will do instead is to smear that out a little bit, because, well, smooth implementation works better practically. It's just a matter of computation and trying. Yes. Yes, so it only integrates over the large. Well, I will now define what this exactly means. Good. So let's define what we will mean by this measure. And what I mean by this measure is the standard path integral measure. Let's say it exists. And then I will add suppression term e to the minus delta sk. Okay, it's just rewriting. I have to tell you now what this delta sk is. This delta sk is a term that is quadratic in the field. And I will define it in momentum space for you. So here I've taken the Fourier transform of the two fields, and I've introduced this RK, which we call regulator function. So this guy is the regulator function. And this regulator function must be chosen exactly to implement this Wilsonian idea of integrating out modes shell by shell. And for that, we have to impose three properties that I will tell you in a second once I have cleaned up the whiteboard. So how you can think about this is basically, well, so it's a quadratic in the fields, right? But it has some non-trivial momentum dependence. So it's kind of a momentum dependent mass term. This is what you may think of if you think of the regulator. Good, so the regulator has to fulfill. As I said, three properties. The first thing that you want to implement is a mode suppression in the infrared. Okay, how do we do that? Well, if you want to suppress modes that are very low energy, you give them a very large mass. Okay, so kind of the minimal property for that is if p squared goes to 0 in this regulator, this should be bigger than 0 so that you gap low energy modes. Usually we use something like RK of 0 is roughly k squared. Okay, so this kind of takes care of the infrared. We also have to, well, partially, we have to impose that the physical IR limit is untouched, right? So as I've told you, when we send k to 0, we want to have performed a full path integral because in the end, we want to end up with the effective action. And here, we want to end up with the standard path integral, which means that this suppression term must just vanish if k is 0. And then there's a third property that we have to impose. It's the UV limit. And this one is a bit subtle. in the end, it's related to the fact that what I tried to explain here, if you can send k to infinity, you want to get back your bare action. It's a bit hard to see at the level of path integral, but the kind of property that you need is that this guy blows up for k going to infinity. There's a lot of subtleties that as I said, some literature on that because it's not unproblematic, this limit. If you want to look in the literature, it goes under the name of the reconstruction problem. I will not discuss this here since it's quite technical and not so interesting. Good. So we have these three properties that kind of should ensure that this picture is implemented. But of course, this leaves a lot of freedom for the actual shape of this function, right? And as long as you keep these properties, you should be fine. You should probably not go too crazy and introduce maybe a second scale at very high energies or very low energies, but anything that is roughly smooth will do the job in the end. Certainly, observables will not depend on your choice of regularization. How does such a regulator function look like? Let me maybe sketch it. What you should have in mind. So if this is p squared over k squared, think of something like this, right? So this is maybe 1. So for low momenta, you want to give modes a mass, something like k squared. For very high momenta, it should vanish. And then roughly at p equal k, it transitions between these two behaviors. That's the kind of idea. For later, let me also plot something different, which looks roughly like this. And this is k dk rk of p squared. Has somewhat similar shape. There's some finite value in the infrared, some peak behavior around 1, and then it goes to 0 again. You understand why I'm showing you this, hopefully, in a few minutes. Okay. So, okay, we've modified the path integral, but certainly we haven't gained anything yet. What we have to now try and derive is a differential equation in this parameter k. Because as I've told you, differential equations are nice, integrals are not so nice. And certainly path integrals are very not nice. Good. So, okay. So we now have this definition, zk. It has this extra regulator term. Okay. What do we do with it? Yes. Yes. No, not really. What? No, it's the same regulator and then the k derivative, the scale derivative. Yeah. No, so the point is that you have to integrate from infinity to 0. And then for k to 0, the regulator vanishes. And terms in the effective, like couplings in the effective action will depend on the regulator, but they are not universal. What is universal are the combinations that appear, for example, in scattering amplitudes. And these, in the end, will be independent of the regulator. Okay. So to make some progress, let's maybe take the KdK derivative of this modified function of this modified path integral. What will happen? Well, if you take a k derivative, the only thing that depends on k is this delta sk. So it's the only thing that we will hit with the derivative. So let's do a short computation. So So since it's an exponential, we just get a k minus k dk of this delta sk, and then e to the minus s phi minus delta sk plus the source term. Okay. Now, what is this delta sk? Well, I've told you already over, let's see, I think over there. It's just quadratic in the field. So let me insert that. I pull out this factor of 1/2 from the definition. I pull out the minus sign from this bracket. What else happens? Insert the form of this guy. This is an integral over momenta. I have minus p k dk rk of p squared phi of p and the exponential. And you kind of already see that maybe this kdk of the regulator might play an important role in what we are going to derive. Good. Can you make any progress with that? Well, yeah, maybe. So we have two occurrences of phi here, and we kind of standard trick. We can write these as source derivatives of the exponential. So what we are going to do next. So copying a lot of stuff. There's momentum integral, there's the k dk rk, and I want to write, as I said, these two fields as source derivatives. Let me just write these also in Fourier space now. And I will not write out the exponential, just you know what is written there. Good. But now I can exchange these two integrals. Well, maybe. Let's assume I can. So I collect the 1 over n, the path integral over this guy. What is this? Well, it's just the second source derivative of the original path integral, right? So I have a minus 1/2. I still have the momentum integral over this k dk rk. And I get the second functional derivative of zk dj p dj minus p. Okay. Now this is already looking better, right? There's no path integral anymore. There's just a momentum integral. And then we have a k dk of the path integral is a second functional derivative of the path integral. So this is already just a differential equation. Well, functional one, but a differential equation. So this is progress. No path integrals anymore. Good. But now we have to kind of go through the same work that we did in the beginning of this lecture, since we do not really want to compute the path integral with z, but we want to compute the effective action. So we kind of have to now go through the same two steps. We have to go to the Schwinger functional first by taking the logarithm, and then we take the Legendre transform. So let's make some space over here. In the meantime, are there any questions? No? Okay. So either way too fast or yeah. Yes. That's part of the path integral, right? I think I wiped it away, but this guy together with the normalization factor is the z. Yes. Hmm? Oh, so that's just bad writing. So there's a minus p here. Yeah, sorry. So what's behind this is just momentum conservation, right? So you have two fields, so they have to have by momentum conservation, you have to have opposite momenta. Good. So now, as I said, the kind of step. Okay, didn't say this is step 2, but this is kind of step 2 over here. And now step 3 is taking the logarithm. So I introduce a wk of j by, well, what is it? Logarithm of zk. And I'm not sure that. Of course, you can now take kdk of this wk and just use the logarithm. Well, derivative of the logarithm is 1 over the argument times derivative of the argument to derive the equation for kdk wk. Good. But in the end, as I said, it's not really this important. What we really want is a flow equation, so a differential equation for this gamma k. And for that, I first have to define what I mean by this gamma k, because there's a slight subtlety, which in the end makes our life a little bit simpler. So I now define this gamma k of phi, which is now a kind of modified Legendre transform if you want. I still take the supremum over sources over what? Well, certainly there's just source times field. I subtract this wk of j, and then I also subtract delta sk. And this is really for convenience. This just makes everything in the end a little bit easier. And I can do that because once I send k to 0, this term vanishes and I still end up with the same standard effective fraction. So as long as this limit is fine, we are good. You can also read this as, so since this guy does not depend on j, you can also push it on the left-hand side, and then you see that the combination of gamma k and delta sk is the standard Legendre transform of this combination. Good. So with this definition, yes, 2 small generalizations of the standard formulas. Let me maybe write that over here. So you first now have that the variation of this gamma k plus delta sk with respect to the field is the supremum source. That's just equation of motion again. And what is the propagator? Well, now we have a k-dependent propagator, which by analogy I define as the second source derivative of this k-dependent Schwinger functional. And you will see that, well, very straightforward analogy. This is now the inverse of this combination. So as in the standard case, you have the second functional derivative of this effective action, now k-dependent. And then since this delta sk is quadratic in the field with a factor 1/2, you just pull out this rk. So what you see as an effect of this extra term is that the propagator is now regularized, right? Due to the properties that we discussed, infrared modes get a gap at finite k. So if you want, this is yeah, thanks. Good. I hope online people didn't miss too much.
Let's go to 24. Now it's good.
Okay, yeah, sorry about that. Just battery running out. Yeah, just to recap, maybe last 2 things. So the k-dependent propagator through this additional RK is now gapped and is finite in the infrared. Okay.
Originally was divergent. How do you see that is divergent?
No, let's just think of a massless field, right? Massless field to leading order has a 1/p² propagator, and that diverges for p to 0. But now you've added this regulator, which has this shape roughly, and certainly it's gapped for finite k. Of course, if it has a mass already, then there's no divergence. Okay, more questions? Yes.
Is there any differentiability requirements for the regulator? Like,
if you want an easy life, yes. The smoother the better, generally. Yeah.
but if it's, I don't know, like very regular, like an exponential to minus x squared, something like that, is it gonna bring more complexity to the calculations, or?
No, that's one of the easy choices, actually. Yeah. Maybe it's, yeah, I think I skipped that actually. I will give some examples a little bit later. Let me just finish the derivation of the flow equation and we can come back to this point. Good. So let's now, from this definition, take again kdk of this expression and see what we get. Okay. So certainly what we get so what's k dependent here? Well, certainly this wk, this delta sk, right? Good. So we first hit this minus kdk wk of the supremum source. We will also hit the regulator term. And in general, the source will also now depend on k. And so we will get two terms. We will get a k dk j. And of course, there will once be a factor of phi from here, sup, and differentiation of this guy. And once again, by definition, this bracket vanishes because the definition of the expectation value is the first derivative of the Schwinger function. Okay. So let's see. So so I didn't derive that, but basically you just insert the differential equation for wk now that you've derived from this step, and you will see that there's a cancellation. Yes.
Sorry, for this last step, actually.
Yeah.
Generating, so the connected generating functional has
Yeah.
a k dependence, but now the field needs to has one.
Yes.
Because
It kind of happens like that. Yeah. So the reason is basically yeah, basically you go through, you use the definition and you basically, it drops out like that the source is also k dependent. Yeah. Good. So once again, I have to skip some steps here, but it's really just plugging in, well, this differential equation into here, plugging this into here, and then you see things happen. What happens is that one term in this differential equation cancels this guy. And at the very end, let me put that over here, we get a really nice equation, differential equation for this gamma k. So what we get okay. We get a factor of 1/2. There will be a momentum integral. And then there will be the propagator and the regulator. And remember that this gamma k, we discussed that over there, is the inverse of the regularized two-point function. So really, this is the central equation of the functional Rg, and this, as Alessia already told you, is called the Wetterich equation. So let's have a good look at it. What does it do? So left-hand side, well, there's just this kdk derivative, so it's a differential equation in k. First order, that's good. First order differential equations are nice. And on the right-hand side, we have kind of a loop integral, what looks like a loop integral, right? It's a momentum integral over a propagator and this kdk of the regulator. Okay, so does this equation make sense? You could ask. And actually it does. It's well defined. So for this, you have to convince yourself that it's well defined in the infrared and in the UV. In the infrared, I already told you, the only thing that could happen is denominators, right? 1/p² or something like that. That can only come from the propagator, but the propagator is regularized, so no infrared divergences. There are also no UV divergences because of the second term, this kdkrk, because kind of by the general properties of the regulator, this carries over to this kdkrk, and this suppresses the UV physics. So really what this flow equation implements is exactly the Wilsonian idea. You're gapping the infrared modes, you're suppressing UV modes, and what you're really integrating out as a specific k are modes with roughly p equal k. So it's exactly what I've told you in the beginning, this picture of shell by shell integrating out modes. Very nice.
It seems that the physics depends on the regulator.
Aha. It seems like that, yes, but it does not at the exact level. So let me stress some properties of this equation. So first of all, we've made no approximation here. This equation, if you do not make any approximations, is exact. It's non-perturbative because we did not do any perturbation theory here. So if you solve this equation, you've solved the path integral. And if you solve the path integral and compute observables, it cannot depend on regularization, as in the standard case. Right? So also in the standard, if in perturbation theory, you introduce a regulator, dim-reg, or whatever you want, hard cutoff. But in the end, your observables are independent, even though in intermediate steps, it looks like you get a regulator dependence. And certainly unphysical quantities will depend on the regulator.
Because if you use two different regulators, you get the same expression.
For observables, yes, not for the effective action. Because the effective action itself is not an observable, but if you compute then a scattering cross section from it, you will get the same answer. Okay, more questions? Make some space. Yes.
So you're saying but you can have different effects.
Yes.
Then am I allowed to take these different effective actions and applying cosmology? Of course, this will be different.
It should not, because as soon as you compute something that is observable, regulator dependence should draw out. For example. No, correlation functions themselves are not observables. It's only you have to work a little bit to get an actual observable. But if you just take derivatives, you don't get right away observable. Like a gravitational correlation function is, for example, gauge dependent. You have to, so that there are some steps in between that we usually put under the rug to get an actual like gauge invariant and nice expression that is really observable.
That the impression that was not due to the correlation. This correlation like from
Yeah,
So
sure.
you are saying that okay, if you take care of precisely the regulators and the details, you should get the same result.
Yeah.
Which I do not see, but is anyone attempted to do this?
Well, so qualifier, the exactness only holds if you don't make approximations. So this equation is, of course, still very complicated, right? So there's basically no way to solve it exactly. So in practice, we have to make approximations. And as soon as you make approximations, you do get a regulated dependence. So that's kind of the, we don't know whether it actually holds. Like we do not have exact computation or exact solutions to this equation. That's the problem. But from the derivation, it should follow that observables are independent of the regulator by construction, because this whole equation is constructed in a way that you get a standard effective action in the limit k to 0. So if you solve this equation, run k from infinity to 0, you should get a reasonable answer. Yeah.
So standard effective action has a nice property that you only need to do 3 level effects.
Yes.
Right. So if you are working with gamma k in between, I mean, would the same statement hold?
The easy answer is don't work with gamma k at finite k, because it's difficult to make sense out of it, because so you break, for example, gauge symmetry in intermediate scales and all kinds of other things happen. You've not integrated out all the modes. So whatever object you have at finite k is a priori unphysical. Now it can happen in certain situations that if you have, let's say, a mass scale, which is, I don't know, 1 GeV, and you've run your flow equation to k below that mass scale, which freezes out everything, the flow is basically 0, and approximately you have some decoupling and you can use the effective action at the finite scale. But it's only approximate.
But right now it's more a tool to get the limit in k.
Exactly. So the finite goal that we have in mind is we want to integrate this equation all the way to k equals 0 and then do standard physics with it. Yeah. Okay, yeah.
Regulator RKT, it depends on which theory we consider.
I'm sorry?
So regulator,
Yeah.
it depends on which theory we consider.
Well, so the only thing that we have to demand is that it's quadratic in the field, right? So for a scalar field, it's just a function of p squared. That has to fulfill the properties that I just wiped away. If you have a vector field, there's an a mu, then it has 2 indices. So this whole thing is really just a 2-point function. Yeah.
There is a typical functional form for regulator when we solving the differential equation.
No, you can pick the functional form. As I said, so you have to satisfy the properties that I've shown you, but apart from that, it's basically your choice. And in some choices, it depends a little bit on the goal that you have in mind. If you want to have a very easy approximation and want to do this loop integral analytically, there's a specific choice. And if you are anyway a very advanced approximation where you have to do this integral numerically anyway, it doesn't really matter. So you can use an exponential, for example. Yeah, mostly arbitrary. Okay. Maybe some more comments. So certainly, I've now discussed this whole thing for a scalar field in flat spacetime because I've used momenta. And in the end, we want to discuss gravity. And momenta and gravity are a bit tricky, right? So what does this really mean? We certainly have to generalize this if we want to do the same thing in a curved spacetime. And kind of the generalization, let me just write it down. First of all, So left-hand side is unchanged. We generalize this loop integral by what we will call supertrace. And what is the supertrace? Well, the supertrace does a lot of things actually. So first of all, if you have multiple fields in your theory, it traces in the matrix space of these fields. Okay, that's a standard trace. If you have a vector field, for example, here, your propagator will have two indices, as will your regulator, and then it has to trace over the three indices. So it's also there just a trace, an index trace. The maybe more involved thing is now this, what is the momentum integral in flat space-time? This has to be generalized, and probably tomorrow one of us will talk a little bit about how you do that in curved space-time. But maybe as a, well, to give you a rough idea, momenta don't exist in curved space-time, but certainly the differential operators exist. So what in the end will happen is instead of p squared or rk of p squared, we'll consider a regulator which depends on some form of covariant Laplacian. So in the end, if you want position space, and if you think about it this way, maybe this operator, we can compute a spectrum, and then if you have the spectrum of this operator, the supertrace really just sums over the eigenvalues. So that makes sense if the spectrum is discrete, can make sense very easily there. And we have to work a little bit harder when the spectrum is continuous. But as I said, we'll probably discuss that tomorrow for a little while. The last thing that this supertrace does is it gives you a minus sign for Grossman valued fields. So if you have fermions or these Faddeev-Popov ghosts that Luca mentioned, you will get a minus sign in front. Okay. So as I said, some more details will follow tomorrow, but there is a generalization. You just have to do the same derivation basically with this slight generalization, but you will arrive at this form. Okay. Good. I just remembered I promised to write down some examples for this regulator shape that are typically used. So one very popular choice is what is called a lithium regulator, which was introduced by Daniel Lithium. That's why the name. How does it look like? It looks like this. We won't. K squared minus Z. Okay, so you have K squared minus a linear term and then the Heaviside theta function. How does it look like? Well, you have P squared, or, well, let me now call it Z because I call it Z above. So it's basically a linear function, starts at K squared for Z equals 0. It goes to 0 at Z is K squared, and then it remains 0 for Z larger than K squared. Very simple, very nice. This is used a lot because it allows you to do this momentum integral analytically in many cases. Disadvantage, well, it's not smooth, right? So this is an issue. Once you do momentum dependence, you will run into trouble at some point. Another choice is, well, exponential regulators, and there are many different choices. The easiest example that you could think of is K squared for dimensional reasons, and then Z over K squared to some power. And that is basically, if you use something like this, this roughly corresponds to what I've shown you in the sketch. So something that's finite, it gives a gap at small momenta, then there's a transition and force off exponentially. I see that both these regulators indeed in this implement both IR and UV finiteness of this flow equation. Okay. Good. So in the last 15 minutes, we will discuss some more properties, and then it's time for the gong show and lunch. Okay. Good. So maybe one more point to also connect to Alessia's lecture. Once again, to stress, this is a first order differential equation in K. And of course, I named this K for a reason, or the reason is that this is really what defines this vector field of beta functions, right? So if you probably see that also tomorrow when we discuss an example, this is what defines the non-perturbative beta functions in your theory. So KdK on the left-hand side is what gives you the betas. Good. Okay, let's maybe do this. So to maybe connect again to scattering amplitudes, you can wonder, well, for scattering amplitudes, it's not really the effective action that we are interested in, but correlation functions. And you can ask the question, well, can I write down a similar flow equation for the correlation functions themselves to have kind of direct access to their computation? And yes, you can. You just take functional derivatives of this equation, right? So let me maybe do the first example. If I take this equation over here in this more general form of a supertrace, and I take the functional derivative of it. Okay, left-hand side is very easy, it's just gamma 1. What happens on the right-hand side? What depends on the field is only the full propagator. Okay? And maybe let me first write down what is the result, and then argue for it. So what you will have is two propagators, a 3-point function, and still this regulator. Why is that? Well, remember that gk is the 2-point function that is regularized. And then if you, inverse, of course. If you now take the derivative of this, you see that you will only hit this gamma k2. And then you simply use the property that if you have x inverse, this is the identity. And if I take the derivative of x inverse, this is 0. And then I use the product rule. So it's dx d phi, x inverse plus x dx inverse d phi. That's still 0. And now I can solve for the derivative of the inverse. And I will exactly, if I plug this in, get this combination. Okay. And now you can take more derivatives to maybe illustrate that. A 2-point function will now hit several terms. You can either hit this gamma 3 and get a gamma 4. Or you can hit either of these propagators, and you will see that you get the same combination. So you get a factor of 2 and you get a factor of minus for this reason. So you get a super trace of gk gamma 3, gk gamma 3, gk, and the regulator insertion. Okay. And of course, you now see the schematics. You just take more and more derivatives of this guy and can directly compute the flow equations for the correlation functions that you need for your amplitude, and then solve for it. Another reason why I've shown this is you see that there is a certain hierarchy in these flow equations for the correlation functions. So The original flow equation of gamma k, only depends on the second functional derivative. Flow equation of gamma 1 depends on the second and third functional derivative. Flow equation of gamma 2 depends on gamma 2, gamma 3, gamma 4. If you continue this, you will see that the flow of the endpoint function will depend on all correlation functions between order 2 and n plus 2. So there's a hierarchy there. So certainly one maybe method to approximately solve this equation is to compute all the correlation functions up to some fixed order n and approximate n plus 1, n plus 2 to get a closed system. Okay. Good. Another thing that I haven't stressed yet is you see that even though we are talking about an effective action in the end, so something that includes all loop effects, we only have a single momentum integral here or a single supertrace. So this is very useful because computationally it's just much easier to have a single momentum integral instead of n, right? But also practically it's just very straightforward to use. Okay. Yeah, let me maybe say that there's actually also diagrammatics attached to this. So kind of similar to Feynman diagrams, we often introduce diagrams to indicate the form of the flow equation. So the rules are propagators are lines. The regulator, so this guy is a circle with a cross inside. This propagator is a line, and the supertrace closes lines. So what this equation means in diagrammatics is I have a propagator, so a line, that connects to this regulator, and I close the line on the other side. And this already looks kind of like a Feynman diagram, right? Same thing over here. For this guy, I have so k, dk, gamma 1. What do I now have? Well, I have a factor of -1/2. I have a propagator. This connects to a 3-point function. This connects to another propagator. And then it's closed via the regulator. Okay, so it's really the flow of a 1-point function. And once again, you have a single loop, even though we include all quantum corrections. And then finally, for the 2-point function, you get 2 diagrams now. The first diagram has a 4-point function instead of a 3-point function here. So basically the same diagram. And then this is a self-energy diagram. And yeah, so there's just some power in this because there's some very systematic way to understand what are the prefactors just by basically symmetries. And it's a bit easier to generate these expressions when you want to compute them. Similar to just standard Feynman diagrams if you want. Good. There's still 5 minutes left. If there are any questions other than that, I would also have one more point. Yes. Yeah.
You said that this combination K partial K
Yeah.
is going to be the generalized function.
Yeah.
But is it clear why this is a sensible definition? Because in a way, I was thinking about that K as the parameter we want to send to 0 to the effect action.
Very good. Yeah. Great question. Thanks. So the definition of, the notion of beta function that we have here is slightly different than the standard definition of a beta function. Yeah. So this was actually connected to what I was going to say now. So the beta functions here are exactly with respect to this fiducial momentum scale. And there's a slight difference here, which leads to all kinds of trouble, but Yeah, it's what when we talk about beta functions, we mean K dependence. Yeah.
K is really square root of K squared. Same.
No, K is just a momentum scale. There's no vector attached to it.
I say momentum scale.
It's a momentum scale or mass scale if you want. But it's not physical, right? It's just a way to integrate out UV modes above this cutoff. It's an infrared cutoff if you want.
Because the beta function of QCD depends on the momentum.
Yeah. So since there are now two questions, let me actually make this point. I think it's also very important to stress this. Since there's sometimes a lot of confusion when we talk about beta functions with the FRG, and people get confused about exactly these points. So what we now in the last 4 or 5 minutes talk about is the physical momentum dependence versus K dependence. Good. So when we say physical momentum dependence, of course, we talk about an effective action and their momentum dependence in this effective action. And in general, this will be different from the K dependence. And good. So I already explained a little bit about this, but maybe to make a concrete example, let's discuss this for gravity. So for gravity, we can certainly now let's make an approximation for this gamma K, right? So we start with the ancient Hilbert term. And then higher orders that I will come to in a moment. So at a practical level, what happens is now all your couplings, will now depend on this K. And they will run with this K, but maybe not necessarily physically. And now what is momentum dependence? Momentum dependence would be something like dependence, as I've argued, dependence on, let's say, a Laplacian. This is physical momentum dependence, right? Let's say if you have a scalar field, this would be a general kinetic term with an arbitrary momentum dependence in position space. Now, what happens in gravity? Let's try to upgrade this K dependence to physical momentum dependence. What happens is nothing good, right? So if I upgrade lambda K to lambda K of delta, well, it acts really on the identity, and differential operator on identity is really just the constant term. So there is no physical momentum dependence in here. Same thing for Newton's coupling, so I have to pull it into the integral to make sense out of it, but it either acts on the identity or it is total derivatives that we don't care about here. So also for GK, we have no physical momentum dependence. So both these, no physical momentum dependence. But they do have a K dependence. So one has to be a bit careful when we discuss these two couplings, what we really mean by momentum dependence. Sometimes, unfortunately, we sometimes use K dependence or momentum dependence for K dependence, but one should really distinguish the two. So you could now ask the question, where is the physical momentum dependence in gravity? And it starts at the second order in curvature. So once I have two curvatures, I can sandwich a function of momenta in there. And of course, this goes on. And now in the FRG, this will not only depend on delta, but also on K. So in a sense, the task for gravity is, if you want to play this game with FRG and asymptotic safety, you want to compute the beta functions of G, lambda, and these higher order terms in K. You want a fixed point at infinite K to get a well-defined theory in the UV. You integrate out all the modes going k to 0, and you read off the correlation functions there to get to the scattering amplitudes. And then the physical momentum dependence is stored here and not there. Okay, any questions to this? Well, that's an R-squared term, right? So it has, so we call this form factor, and the momentum dependence is in there. So of course, for a local theory, if you only have finitely many derivatives, and that there's in the end the momentum dependence also in curvature. If you write it in terms of metric, there's DDG. But if I speak about momentum dependence, I usually mean a general momentum dependence that then translates for scattering amplitude in some S and T dependence. And curvature only gives you two derivatives always, whereas this gives you, in general, some arbitrary power.
Maybe if you come to some scattering amplitude,
Mhm.
my scattering amplitude comes from momentum.
Yeah.
What are the
No, I mean, you simply take this effective action with all the higher terms that you need. You take the correlation functions of that. And then if you go to a flat background, as both Luca and Anna did, you can go to momentum space then, and all these Laplacians go to p squared. So it's really in these functions plus some extra kind of trivial momentum dependence, which comes from the expansion of the curvatures, but kind of the really non-trivial momentum dependence comes from these general functions. Which, of course, you can also think of this in the easiest case as some Taylor expansion in powers of delta, but certainly already at one loop level, there will be a logarithm here.
calculation is also in code?
Yes, yeah. So this delta is really minus g mu nu d mu d nu. So this is covariant. The effective action must be covariant, so it has to respect the diffeomorphism symmetry.
Then there is some non-trivial curvature in the background.
No, I've not introduced any background here, right? So this is just a function of a single metric. Once we are computing, things are getting involved, but in the end, what you should get is a function of just a metric, and then you can take, if you want, take correlation functions in flat background to compute standard scattering amplitudes. But you first have to take variations in general. So variations will also hit this function. You get derivatives and so on. And then you can go to a flat background.
I mean, if you use this regulator,
Yeah.
You have p squared over k squared. So you are eliminating the p squared.
Yeah. So what this flow equation really implements is if I go from k to k minus delta k, I integrate out modes which have a momentum roughly k. If I think of momentum space. And of course, if I think of eigenvalues of operators, it's the same thing. I'm integrating out eigenvalues roughly k squared.
I was thinking if you get in string theory, you have also an exponential cutoff, but instead of k, you will have a right.
No, as I said, this regulator is completely arbitrary. No, not completely, but basically arbitrary. And you pick whatever, as long as it fulfills the standard criteria. So this is really, the exact shape is completely unphysical. Yeah.
The regulator says it is physical indeed,
Yeah.
but it can still appear in different action. So if you
Yes.
take two different regulators, you have two different actions. If you take difference between two effective actions, define two different regulators, you get something that is proportional to the equation that one shell would give you 0.
I would think so. I mean, so this regulator dependence is really just scheme dependence. So I would So not having thought about it for long, but that sounds reasonable.
Fine, better equation, this one with
Mm.
one regulator, another one with another regulator, take the difference and then compute formula, I don't know, like some example, you don't say it must be.
Unfortunately, it's not so easy because if you change the regulator, you change the starting point. Remember that, I mean, so this microscopic action, I told you a little bit like hand wavy, that there's some problem going on there to define this in a good way. And really what happens is you're kind of shifting a little bit where you're ending up. So it's not that easy to just take the difference of flows, unfortunately, to get towards the same effective action in the end. Yeah. Okay, no more question. I think it's time for the gong show. What's that problem? It's not touching.